Look at the far edge of our solar system, 30 times further from the Sun than Earth. Out here in the dark, you'll find Neptune. At this distance, logic suggests a world of total stasis, a frozen sphere where the lack of solar energy has left the surface geologically dead for billions of years. However, when the Voyager 2 spacecraft reached this distant orbit in 1989, it recorded a reality that ignored our models of how a cold planet should behave. Neptune's atmosphere is a place of chaos, hosting massive, planet-scarring storms and winds that whip around the equator at over 1,300 miles per hour, speeds that exceed supersonic slow. This creates the central mystery of the outer system: why the coldest, most distant realm of our planets operates the most violent weather engine in the solar system. The cloud tops of Neptune are appropriately hostile, plunging to -361 degrees Fahrenheit. This chart maps the thermal budget, showing Neptune radiates 2.6 times more energy than it absorbs. This rising internal heat pushes against the freezing outer atmosphere, forcing bands of gas in opposite directions, shearing to create the solar system's fastest winds. Unlike Jupiter's Great Red Spot, which has remained stable for centuries, Neptune's dark vortexes are transient. They appear, migrate across latitudes, and vanish entirely within a few years, suggesting an atmosphere in a state of constant, high-energy flux. Neptune operates as a violent atmospheric engine, powered entirely by an unexplained furnace hidden deep within its interior. Astronomers classify Neptune as an ice giant, though sinking beneath the cloud deck reveals a world that is far from solid. Immense pressure crushes water, ammonia, and methane into a hot, highly conductive supercritical fluid, the planet's actual surface. Deep within, molecular bonds break. Carbon atoms crystallize and sink, creating a continuous rain of solid diamonds falling like hailstones through the glowing mantle. This churning fluid generates a lopsided magnetic field, tilted at a 47-degree angle and offset from the planet's center by over 8,000 miles. Because of this misalignment, Neptune's auroras do not cluster at the poles. Instead, glowing auroral rings form unusually around the mid-latitudes. This hidden interior is a place of extreme pressure and electromagnetic chaos, completely masked by the planet's quiet blue exterior. Neptune's influence extends outward to Triton, a moon that does not belong in this system. This orbital map shows Triton moving in the exact opposite direction of Neptune's rotation. This retrograde orbit identifies Triton as a captured Kuiper Belt object, a wandering world snatched by Neptune's gravity millions of years ago. Despite surface temperatures of -391 degrees Fahrenheit, Triton remains geologically active. Pressurized nitrogen violently erupts through the frozen crust as towering geysers. But Triton is currently locked in a decaying orbit. It is spiraling inward, and in roughly 3.6 billion years, it will cross the Roche limit and be shredded into a massive new ring system. Triton serves as a real-time demonstration of Neptune's destructive gravitational dominance over the far reaches of the solar system. On a larger scale, Neptune functions as the primary gravitational engine for the entire outer edge of our neighborhood. Neptune's gravity dictates the structure of the Kuiper Belt. It locks Pluto into a strict mathematical resonance, forcing the dwarf planet to complete exactly 2 orbits for every 3 of Neptune's to ensure the two never collide. Neptune serves as the primary gravitational architect of the solar system's edge, dictating the orbital logic of everything in its wake. Most of our detailed knowledge of this planet was gathered during a single weekend in August 1989. Since the Voyager encounter, astronomers have monitored Neptune's changing weather from billions of miles away using Earth-orbiting tools like the Hubble Space Telescope. The data we gather continues to challenge our understanding. The planet's internal heat and its misaligned magnetic field are anomalies that do not fit our standard models of planetary formation. The outer reaches of our solar system exist as active laboratories of extreme physics, and Neptune remains our most challenging.